Hello everyone, welcome to data structure class. In this unit, we will introduce complexity analysis. As you may know that we can achieve the same goal by developing different algorithms. For example, assume we want to calculate the sum from 1 to n, where n is a large number. The first approach is that you can develop a loop as shown on the screen to add all numbers from 1 to n. And the second approach is that you can use a formula which can simply plug in the value n to the equation to obtain the sum. Based on your observation, which approach is more efficient? Obviously, the second approach is much faster than the first approach, especially when n is a large number. In order to evaluate the performance of algorithms, we need to develop a way to compare algorithms in a fairly manner, which leads to the development of complexity analysis. You may wonder that I can simply run the code on a computer and measure the execution time. Indeed, this strategy allows you to compare different algorithms on the same machine. However, assume you create the same algorithm in different programming language, you may still get different execution time. Not to mention the performance of the computer may have great impact on the time of execution of a program. Therefore, the complexity analysis should ignore the low-level details such as language, hardware, or the instruction set of the given CPU. To analyze the complexity of an algorithm, we use Big O notation to describe the worst-case scenario performance. Here, we list the most important 9 Big O notations with their names and examples. The Big O notation describes the time complexity of an algorithm when handling data of size n. As you can see on the screen, Big O of 1 is a constant time. For example, accessing an array element is considered as Big O of 1. Also, access any value in the memory is also Big O of 1. So you may consider Big O of 1 as the unit time. Another example is Big O of n. The Big O of n is the linear time. For example, if you have an array of n elements, assume you want to find the minimum value in an array, you must access each array element at least one time. And thus, you need at least Big O of n times 1, which is equal to Big O of n. This indicates that when the number of array elements increases, the execution time increases proportionally. Similarly, when you have a two-dimensional array of size n by n, the time increment is not growing and linear. For example, assume n equal to 10, you will have total 10 by 10 equal 100 elements. If you double the n, which is 20, you will have total 20 by 20, that is 400 elements, not 200s. You can see that the array element is not proportionally increased. In the list, we color-coded each Big O notation as green, yellow, or red. If an algorithm belongs to green, the algorithm is considered as efficiency. If an algorithm is classified as yellow, the algorithm is considered as slow. And an algorithm is grouped into the red one, the algorithm is bad. For example, we have developed two recursive functions in our homework. That is the Fibonacci and permutation. You can test Fibonacci function with a relative large n, or test the permutation with a relative longer string. You will see the execution time becomes very slow. This is an example code for big of 1. As you can see, we assign a value to a variable in the memory, which is considered as big O of 1. When we display the value stored in the variable, we access the value from the memory, which is also considered as big O of 1. As you can see, each statement in this example is big O of 1. The total time should be big O of 2 times 1, which is big O of 2. However, in the big O notation, we only differentiate algorithm at different levels. Big O of 2 is still considered as in the big O of 1 level, and thus the time complexity of the above code is still big O of 1. This is an example code for big O of n. As you can see, we create a loop to iterate from 1 to n. In this example, we increase the loop variable I by 1. In each iteration, we display the variable I. When we display the value stored in the variable, we access the value from the memory, which is considered as big of 1. As you can see, the variable will be displayed for n times, and thus the total time should be big O of n times 1, which is equal to big O of n. In the big O notation, n typically refers to a large number, and thus the time complexity of the above code is big O of n. You can consider the big O of n time complexity as a baseline where the time complexity and the number of data points increase proportionally. This is an example code for big O of log n. As you can see, we create a loop to iterate from 1 to n. However, the increment of loop variable I is not linear. In this example, we double the loop variable I in each iteration. When we display the value stored in the variable, we access the value from the memory, which is also considered as big O of 1. As you can see, the value in the loop variable I increases quickly, so that the total time to complete the loop should be big O of log n times 1, which is equal to big O of log n. It is worth mentioning that big O of log n is faster than the big O of n, which is the baseline execution time. In this example, we have a nested loop. While the outer loop repeats n times, and the inner loop repeats log n times. And thus, the time complexity is big O of n times log n times 1, which is big O of n log n. This code exemplifies a big O of n squared. As you can see in the nested loop, the outer loop and inner loop both repeat n times, and thus the total time complexity is big O of n times 1, and thus equal to big O of n squared. Similarly, this code exemplifies a big O of n cubed. As you can see in the nested loop, all three loops repeat n times, and thus the total time complexity is big O of n times n times n times 1, which equals to big O of n cubed. As you can see, the n cubed should be very slow, especially when n is a large number. In the Fibonacci recursion function, the time complexity is 2 to the power of n. And if you remember that the number of permutation for a length of n is the n factorial. So the permutation algorithm is n factorial. This graph summarizes the performance of all big O notations. The line in green is the baseline, which is big O of n. You need to remember the performance of each big O notation, which one is fast and which one is slow. In the graph, if a curve is more torovertical, the time complexity is high. While a curve is more torohorizontal, the time complexity is low. You need to know their ranking in terms of the time complexity. Questions?